Now announcing OpenMDAO Release 3.37.1, which includes features for automatic differentiation brought to you by the OpenMDAO team and Google's JAX library. You can get access to these features today by pip installing OpenMDAO all, or by pulling the latest 3.37.1 release and reinstalling with the all options. And if you think that auto differentiation will make your workflows more efficient, please hit that like and subscribe button. Welcome to the OpenMDAO channel. My name is Elliot Aretskin-Harriton, and I am from NASA's MDAO team. I've been using OpenMDAO since 2017 when I started modeling the performance and optimization of star trackers and tilt-wing aircraft. Since then, I've been using it constantly to help advance the state-of-the-art in optimization and uncertainty analysis. Most recently, I've been breaking this JAX update so that you, our users, are going to have an easier time when you start using it. This video is broken into three parts. First, we're going to talk about the pros and cons of using JAX components. Then we're going to go over some of the useful functions that JAX and OpenMDAO provide for use with automatic differentiation. And lastly, I will show you an example of those functions used to convert an OpenMDAO explicit component into a JAX explicit component. So let's talk about the pros and cons. In the pros column, because JAX provides automatic differentiation, that means that the user does not have to provide their own analytic, finite difference, or complex step derivatives. Additionally, you don't have to worry about making your functions complex safe, and you're still going to get really high accurate derivatives. And you're going to do this by using and leveraging the JAX NumPy library, which we are going to refer to in the rest of this video as JNP. Calculating the derivatives automatically can potentially save users a lot of time when it comes to updating your functions. So if in your compute function a couple years down the line you need to update that, well, you don't have to worry about rederiving your analytic partial derivatives for that. Instead, you can let JAX handle that. The JNP library contains a host of differentiated functions, and we're going to go over those in the next section. Now let's talk about some of the cons. Using JAX for your derivatives is potentially slower than analytic. Now, we really have to do some further investigation on this. Maybe if one of the community members wants to do that, I would highly encourage it. There's a possibility that having a lot of GPU compute available will actually mean that JAX has a faster ability to compute your derivatives than analytic. This is yet to be seen. Additionally, when compared with working with, say, regular NumPy arrays, working with JAX arrays can be slightly more tricky because we cannot simply pick out values in those arrays and replace them. We have to make sure that these arrays are consistent and that JAX can properly trace every change that's happening to that array in order to be able to construct the partials automatically. Additionally, you're going to need to think about the JNP functions that you're using and if those functions are smoothly differentiable or if they're discontinuous. If those functions are discontinuous, then you may have problems with your optimization as that optimizer is unable to find a slope at particular places in the solution space. So these JNP function calls, they're going to be very powerful, but you have to be cautious with them. Next, let's talk about some of the useful functions that both the JAX NumPy and the OpenMDAO libraries provide to you to make your experience in auto differentiation a little bit smoother. So on the left-hand side here, we have everything that's supplied by the JNP library. These are things like exponent, log, cosine, sine, tangent, square root, atan2, sum, mean, jnp.where, which is interesting. We'll talk about that in a moment, and lineage.solve. So as you can see, a lot of these are smooth and have smooth derivatives, but some of them, like atan2, are discontinuous depending on the inputs. Both atan2 and jnp.where can be discontinuous. And so you have to be cautious. If you have a lot of those in your code, maybe you're going to be stepping over that discontinuous point a lot, and that may cause your optimizers some problems. Now, the JNP linalg.solve, you're going to want to be cautious when using this if you're trying to solve things in reverse mode and you have large matrices. That is going to cause a huge slowdown in your code, and you're going to need to do something a little bit more complex. If you have small matrices, in the example that we have a like a 5 by 5 or a 6 by 6 matrix, linalg.solve is going to be your go-to for doing a linear solve for that matrix. Some additional utility functions that the JNP library supplies us are uh, jnp.array, jnp.asArray, and jnp.grad. So .array is going to allow you to create essentially like NumPy arrays, but they're JAX NumPy arrays, and that will work well for any elements that you know are already of a JAX array or vector type. For the jnp.asArray, I actually use these whenever I don't exactly know the type. Like I have scalars, I have some arrays, I want to just kind of toss them all together and get an array, a JAX array out of that. I'm going to be using the jnp.asArray for that. And lastly, jnp.grad, that is going to help you understand the gradients that a particular function has. So if you stumble across a function that isn't here in the JAX NumPy library or elsewhere, you can toss it into jnp.grad, and you can use that to get some information on, is that function smoothly differentiable or not. Mind you, there are also, there's AI programs that can help you understand if something is smoothly differentiable or not, but jnp.grad is a great way to verify for yourself. Now, let's switch over to the OpenMDAO functions that are supplied. We have OMJ, so OpenMDAO.jax libraries, and so omj.ksmin, ksmax, we have made sure that these libraries can take in JAX arrays or JAX arrays with scalars, and they are going to look for the maximum or the minimum point in that entire array and give that back to you in a smoothly differentiable function. Now, if you are using jnp.max or jnp.min, you are not going to get a smoothly differentiable function, and then your optimization is going to crash, and we don't want to see that. So we're trying to help you out. So we have the ks min and maxes. Those are specifically going to be for like array inputs. You have a bunch of inputs. You're trying to find just the one value that's the min and the max there. omj.smoothmin and .smoothmax, these are going to be in cases where you have just say like two inputs and you're trying to compare them to understand which is the max, which is the min. omj.arctanh, this is going to be an activation function. And there are some great examples in the OpenMDAO docs about how to use that, as well as all of the other smooth components here that we're supplying for you. Let's see, the last one here that is one of my favorites is .smoothRound. If you need to have integer increments of things, you have one engine, you have two engines, you have one gearbox, you have two gearbox, .smoothRound is going to be able to help you get to that. It's going to be able to help get to that integer value. Last but not least, for utilities on the OpenMDAO side, we have the options. So this is an option you can declare in setup. This is the option use JIT equals not debug. And the way that that's going to work is essentially you can turn debugging on and off by setting that to true or setting your debug flag to false. And in that case, you can just use regular Python print statements, which is my preferable way to debug. It makes things simple and easy. On the OpenMDAO side, we have a couple of help docs here in the OpenMDAO docs, which are going to walk you through how to use each of these available functions. We have some code examples here for you as well, and then we have some nice graphs to show you exactly how these are working. And we have these all for the, the smooth absolute value, the smooth mins, the smooth maxes, and so on. Now let's see some of this in action. We'll pull it all together and we'll show you this in action in an example gearbox component. So here we have part of our gearbox component. This component was originally designed in MATLAB, so there are some if statements in it. It was then converted into an OpenMDAO explicit component, and now we're going to take that and convert it into a JAX explicit component. First things first, I'm looking at the top of the file here, and we are importing NumPy as NP, and we actually want to replace that with jax.numpy as JNP. And we want to make sure that this fix is switched throughout the entire code base. So we are going to look for any case where we are using NumPy, and we are going to replace it with JNP. 21 cases changed. That's fantastic. Next things next. I noticed that we're importing the math library. I don't want to have anything to do with that library, in that library is not going to work for us. We also need to replace everything from that library with the JNP library. So that's another 9 instances. Great. So with that started off, we're going to remove that guy there. So with that started off, I'm also going to import the OpenMDAO JAX library. And we're just importing that as OMJ. There we go. Now over here in setup, the typical way that OpenMDAO works is anytime you add an input and you don't specify a shape, that input is going to be imported into the rest of your compute primal or your compute as a NumPy array. Now, if you want to instead change that default shape to be scalars, you can use this set of code in the initialize part of your class in order to set the default shape to a scalar. This is particularly useful when you're trying to concatenate arrays, and it prevents you from having errors like all inputs must be the same shape, which I received multiple times when using ksmin and ksmax functions. I'm going to set up a little debugger flag here. And this is useful if you want to be able to just write regular print statements in your compute in order to get those to show up, which is one of the ways that I use to debug. And as a partner to that, you're going to need to make sure to use the options of setting JIT right here in setup. So this is, once you set this to true or false, that's going to enable or disable JIT, and then we're going to be able to see those print statements. Next things next, I'm going to look at these inputs and the outputs to the component. Now, I'm not going to change them, but I do want to make note of the order, because the order for both the inputs and the outputs is going to matter to us. Down here at the setup partials, we no longer need to declare those. So we're just going to go ahead and delete that, which is really exciting. Oh, and of course, we need to inherit not from OM explicit component, but OM JAX explicit component. So there we go. We've set that up as well. Now going down to the compute, this compute actually becomes a compute primal. So there are some differences with compute primal, specifically the way that you put your inputs in. So we're going to go back here to our inputs, and we are going to start grabbing those. Torque is my first input. RPM is my second input. We are going to grab those, and we are going to put all of those here in compute primal. Just the inputs. They need to be in order. If they're not in order, JAX is going to yell at you. The same thing with the outputs. You're going to write a return down at the bottom of this function, as opposed to defining your outputs like this, which is traditionally how we define them for OpenMDAO explicit components. We're not going to do that at all. And instead, we are going to make a return function, which is more traditional. And then we are going to have to return our outputs in order. Once again, so for example, motor mass is our first output, so we're going to make sure that that is output first, and so on and so forth. If you do not get these in the right order, JAX will also yell at you. Okay, so now that we've got some of that out of the way, we can see we have almost 20 lines of code here that is just re-aliasing things from inputs to more accessible names. We can just delete that. All of these are now going to be available from the compute primal, so we can go ahead and take all of those out. For some of these where we have calculations, we're of course going to leave those in. Next things next, I'm going to go in here and I'm going to start looking for places where we're using things like absolute values. So ABS, let's see, that's the only place for ABS? Okay, so we no longer want to use just a standard ABS. We want to make sure to use the omj.smooth ABS. That's really important. That's going to give you your smooth absolute value. Additionally, any place that we have max, we don't just want to use the max function. We want to, and it look like there's a lot of names here. We want to make sure that we are using, let's see, there's 4 instances. Yeah, we are going to shift this max function again to omj.smooth max. And actually, I am not going to use the smooth max because I don't know necessarily the size of these vectors. Maybe there's 2 elements that we're maxing. Maybe there's an array. So in that case, the KS max is going to be easier for me, and that's more likely to work. So let's go ahead and wholesale replace all of those. We're going to do the same thing with the min. Look for, oh, it looks like we're not using min anywhere. So that's exciting. There's some names in there, but not actual usage. So that's fantastic. Now, coming across if statements. Now, of course, normally you don't want to have these in your OpenMDAO components. However, we do have a way of handling this in JAX. Specifically, we can use the jmp.where to replace these values and essentially act as an if statement. So this is not necessarily differentiable, but it can be done. So the way this works, we're going to take our trigger, or essentially where this happens, which is when slot -2 times t bobbin is less than 0, and then what happens? The t bobbin value becomes that. Otherwise, t bobbin probably stays the same, and so we're just going to assign that like that. So this is how you go ahead and replace these if statements. You have your activation. When the if statement triggers, you have what happens when that trigger happens, and then finally what happens if it doesn't happen. You have to assign both what happens when it happens and what happens when it doesn't happen in order um, to properly have full traceability through both potential chains. Now, this is not necessarily differentiable, and so this is one of it. It's not that it's not necessarily differentiable. It's not necessarily smoothly differentiable, so it could be discontinuous, and that's all about how these two kind of functions, slot w over 4 versus t bob, and how those come together at the transition point. So you may need to be cognizant about that. If you have troubles where the optimizer is choking because it is flipping back and forth on these values because it is not smoothly differentiable, you may want to change this to the OpenMDAO activator function, which I believe is arctanh. You can change it to that, and that will be smoothly differentiable. Okay, so let's find some more interesting cases here. I know that we have some interesting matrix math down here at the end. So this is actually matrix math encapsulated in an if statement. So what we can do here, what you're gonna notice here for this is a similar type of matrix assignment that we do want to make. These like J and P dot array functions. Now, I'm not yeah, these float calls are not going to work well. So we are actually going to take those float calls out. And we don't actually know right now. I don't know off the top of my head of are these going to be JAX arrays? Are these going to be scalars or something like that? So I'm actually going to call this as array as opposed to jmp.array. As array is going to be a little bit more forgiving as far as you're going to be able to toss in your scalars, your JAX arrays in there, and it's going to be able to build an array out of all of those things. Now, notice here we build this array, and then we do a linealge solve with this second array, this Q vector array. Now this is definitely not how we want to assign arrays when it comes to JAX. Basically, we're assigning an array of zeros, and then we are poking individual values into that array. And JAX is not going to like that. That is not going to work well for differentiation. So the way that we're actually going to replace this is we are going to just say, hey, my Q3, this is just this value. We're going to make individual calculations. We are not going to pre-assign this vector. So we are not going to say JMP.zeros. We are going to have to assemble this as as one array, all at the same time. So I'm actually going to assign each of these elements separately, right? So we have our Q3, which was this, the resistive loss. We've taken care of that. It looks like we have our 0, 2, 4, and 5, which is this over here. So I'm going to call this just Q0. We're going to call that that. And then it looks like we have, and then we're poking new values into 4 and 5 as well. So we are going to call that Q4 and Q5. And what we're doing here, we're going to do these calculations individually, and then we are going to assemble the entire matrix as all at one go. So we're going to say jmp.asArray, and we are going to put this all together. So we know the first element is Q0, second element is Q0. Oh, this is zeroth first and second element. Those are all up. Oh, this is Q_0, of course. So those are all Q0 elements. And now our third element is actually going to be this. It's going to be our Q3, and then we have our Q4 and our Q5. And so this will work now, as opposed to that other method. So this will work because we've taken those individual calculations, we're doing those calculations one at a time, and then we're assembling an entire matrix. Then notice we have this jmp.linealge.solve. Now this matrix is small. It's yeah, I think this is R is like a 6 by 6, Q is a 6 by 6. So this jmp.linealge.solve here, this is going to be okay. It's not too large. It's not going to slow things down too much. So don't worry about that. If this R matrix, this RMAT matrix, if this was huge, if this was 100 by 100 or something like that, you may need to take this linealge.solve and essentially output your R matrix and your Q vector. You may have to output that from this component in the return value down here at the bottom. And then you may have to do essentially a separate solve in OpenMDAO in order to successfully do that efficiently. That's the key thing here. Okay, so going further through, we have this jmp.log. That's totally fine. jmp.square root. We're happy with those. We have some more if statements. Again, we are going to replace a lot of those if statements with the .where functionality. Now, this in this particular case, this researcher has made an essentially a solver here. This is 2 iterations of a solver, and basically said, look, it's basically going to be about converged by the time that it gets the second iteration, so don't worry about it. Something like this, we actually use this multiple times in this code. We can actually go ahead and create a utility function for something like that. So here's a number of the utility functions that we've made, and these are essentially just these are JAX functions. They look very much like Python functions, but they're JAXified, right? We're using our JAX libraries, that sort of thing, and we're just we can use these, we can reuse these throughout our code to shorten our code length, right? So I don't have to have this in here 5 different times. I can just toss in my util function, and then call it here, and that will speed things up for us, make our code nice and compact. Again, we have an RMAT matrix that we're assigning individually. That's fine. We don't want to see any of those float calls. That's not going to help us in this case. We're going to remove those. And then we have another Q vector and R matrix and another lineage solve. So we would sort out this Q vector. Again, we can't declare it like this. In the return function, remember, we're going to have to return things in order, like I mentioned above. So whereas our motor mass was our second item, our motor efficiency, sorry, our motor mass was our first item, our motor mass is our second item, there we go, motor efficiency, and so on and so forth. We're going to make sure to return all those items in order. All right, so that's a quick example of one of the ways that you can take and leverage our JAX.numpy and OpenMDAO.JAX libraries to convert some existing functions, or perhaps rewrite from scratch some of the existing functions, and make them JAXified. With this integration of OpenMDAO and JAX, we hope that we've provided an avenue for you, our users, to make components faster, to maintain those components easier, because you won't have to update those derivatives if your computes change in the future. There are some intricacies, as we've seen with using JAX, but overall it's very similar to bare coding with NumPy, with a few exceptions. As always, if you have questions about OpenMDAO, please go to our OpenMDAO Stack Overflow and ask questions. There's a large community there that can help answer questions if the devs don't have time to answer them ourselves. If you have something cool that you'd like to contribute back to OpenMDAO, please look at our POEM process, which is our official process for submitting updates to OpenMDAO. It's up on GitHub, and put together a pull request. We appreciate community involvement with us to help make the code base better for everyone. That's the update for today, guys. Until next time, may your constraints be few, and may your solvers always converge.